My name is Sebastian Diaz, and I'm pleased to have this opportunity to tell you about our latest work on Chiral Hinge magnons in second order topological magnon insulators. I am currently affiliated to the University of Duisburg-Essen in Germany in the TWIST group led by Professor Karin Eberscher-Sitte. But this work was conducted while I was a postdoc at the University of Basel in Switzerland in the group of Professor Daniel Loss. For details of this work, please check out our recent Physical Review B. Let me begin by sharing my excitement about our discovery of a novel state of matter in 3 dimensions with remarkably robust Chiral Hinge magnons. Here you can see a 3D sample of a ferromagnet, and highlighted in yellow, there's a path followed by a magnon that propagates unidirectionally. This path is located at the hinges of the sample, hence the name, and the hinges are where the facets of the sample intersect. This discovery is of course of importance for magnonics, the harnessing of magnons as information carriers, especially now that magnonics is trying to explore possibilities to go into the 3rd dimension. Magnons used to be considered these trivial excitations of magnetic systems, but lessons learned from topological matter have taught us that it's also possible to have topological magnons. For example, in 2 dimensions, it's possible to have first-order topological magnons. That corresponds to the case where the bulk of the sample is trivial, but there are topologically protected magnonic edge states, here highlighted in orange. We did a bit of work along this research direction, and we identified that both antiferromagnetic and ferromagnetic Scherman crystals are suitable platforms to realize first-order topological magnons. These topologically protected chiral magnonic edge states are unidirectional channels for magnon spin currents that can be controlled by magnetic fields and of course are useful for magnonics applications. In the literature on topological matter, there's also the concept of higher order topological states, meaning states localized at the higher order boundaries of the system. Here I'm showing the case of a second order topological magnonic system in 2 dimensions. That corresponds to a 2-dimensional sample that has no magnons, but robust topologically protected magnonic states appear at the corners, here highlighted in orange as well. And we proposed that such states can be realized in anti-Scherman crystals. These anti-Scherman crystals were already realized experimentally in Heusler compounds. Now, we were wondering, what would a second-order topological magnon in 3 dimensions look like? And for that, let's first consider our 3-dimensional sample. Following the logic of higher-order topology, that would correspond to magnons that localize along the hinges of the sample, here highlighted in orange. That's where the facets of the sample intersect. And I'm going here to show you how we can construct a model that supports such hinge magnons. And we begin with, as building blocks, ferromagnetic layers with Yaroshinsky-Morier interaction, which are known to host edge magnons, topologically protected edge magnons. And we're going to stack layers with opposite sign of DMI alternating. And we're going to get this big stack of those. A concrete realization that we have in mind is a honeycomb ferromagnet, where here I'm showing in the bottom in red and blue the 2 sublattices that the honeycomb ferromagnet has. The spins are going to be sitting in those sublattices. And in the yellow sides denote where the topologically protected magnonic edge state would be mainly localized. This is what the stack of such layers would look like. Here we're looking at one of its side facets, And let me call your attention to these vertical chains, where I am showing one for the blue and the one for the red sides. And please notice that the way we are coupling them along the vertical direction is through an alternating exchange that is forming a dimerization pattern. So there are strong and weak bonds. Using Holstein-Primakov transformation and standard linear spin wave theory, we can construct the band structure of the magnon supported by this model. And first, let me show you what the bulk magnum band structure looks like. Shown on the left, there are 4 bands because our system has 4 spins in the magnetic unit cell. And we see already here the presence of a gap highlighted in yellow, and that's because our system has TMI. If we project that bulk spectrum onto a facet, a 2D surface, we get this band structure on the left, and we see that there's also a gap, a surface gap, highlighted now in yellow, and this gap is present because of this dimerization pattern in the exchange along the vertical direction. And that is controlled by this parameter delta J perp, also highlighted in yellow on the right. This parameter acts as a sort of mass for the gap. The gap closes when delta J perp vanishes. If we further project our magnonic band structure along a 1 dimension, we find that within the gap, 2 states emerge, the 2 orange states, and they correspond to hinge magnons. So here on the right, I am now showing a finite size sample with an odd number of layers and obtained using exact diagonalization. There's here highlighted in orange a hinge magnonic state. You can see that there are 2 hinge magnons with 2 different slopes. Those correspond to the vertical hinge magnons shown on the right. And because they have different slopes, they propagate in opposite directions. One is going upward and the other one is going downward. How do I know that they indeed propagate unidirectionally, that they are chiral? Well, to check that, besides just looking at the different slopes in the band structure, we employed atomistic spin simulations for different systems with odd and with even number of layers. And we excited the system with an oscillating AC magnetic field at one site of the sample, and you can see that clearly the magnonic excitation propagates unidirectionally along a path that follows the hinges of the sample, and the actual path depends on the number of layers. This Chiral Hinge magnon is very robust, remarkably robust, as you can see when we incorporate a defect here in the sample. The hinge magnon just goes around it and continues propagating unidirectionally. We further check the robustness of the hinge magnons by introducing disorder and breaking crystalline symmetries in our model. Irrespective of that, the Chiral Hinge magnon remained quite robust. But now you may be wondering, what is the physical reason, what is the physical intuition behind the emergence of these Chiral Hinge magnons? Here on the left, you can see the Chiral Hinge magnon obtained from exact diagonalization. And let's take a cross-section, which is shown on the right. It's, as you know, a honeycomb lattice, and there are blue terminated and red terminated edges, which are indeed facets. I will now make the argument that those facets host vertical Schrieffer-Heeger chains. So for an odd number of layers, here I have two cases. On the left, when delta J perp, this parameter that controls the dimerization pattern of the vertical chains, is positive, using what we know about the SSH model, there are topologically protected end states that, in the case on the left, appear at the top. But when delta J perp is negative, as shown on the right, those end states are going to be localized at the bottom. And now let me remind you of the distinction between the blue and the red sublattices. They have an alternating dimerization pattern, and they can be related in the following way. So if the blue one has delta J perp positive, then you can get the red one with the opposite sign of delta J perp. So now, here again is the cross-section. There are two regions, one with positive delta J perp in blue and one with negative delta J perp in red. And where they meet, that's at the obtuse corners of this cross-section, that's where we have a domain wall, when we change the sign of delta J perp. And it's known in topological matter research that when that happens, when we have a mass parameter that changes sign, then at the domain wall, there's going to be a zero mass state. And that corresponds to our vertical hinge magnon. So I'm going to show you the facets corresponding to this region highlighted in gray. Here you have it. So on the left, we have the blue terminated facet with positive delta J perp, and then the end states are located at the top layer. On the right hand side, you have the red terminated facet with negative delta J perp and end states localized at the bottom layer. And the domain wall, that's where you can observe this zero mass vertical state, which is the hinge magnon that connects the top and bottom portions. Now that we have an understanding of why and how these Chiral Hinge magnons emerge, we can play and engineer the edge termination, the facets terminations, also modify the number of layers to obtain various paths for our Chiral Hinge magnons, which could be of advantage for magnonic applications. Let me now propose an experimental realization for our system. So we start with a layer of chromium and iodine and bromide. This is a Janus monolayer, which is known to have Jeloshinsky-Morin interaction. And we are also going to have a chromium tribromide monolayer, which is known to have no DMI. This is no problem. We can relax this condition in our model. So we have one ingredient, we have the DMI, which opens the bulk gap, but we still need to have this dimerization pattern that is crucial to open the surface gap. And we can do that by using transition metal dechalcogenides. So we're going to have two TMD layers. So for the sandwich of the TMD and the chromium ion bromide, we are going to have a situation as the one shown on the left. Here you have in red and blue the sites of the chromium, and on top of the blue site there's a chalcogen atom. You can think of the case of, for example, a TMD being molybdenum diselenide, and here this yellow atom would correspond to the selenide atom. Now for the other pair of layers, we are going to flip the transition metal dechalcogenide so that now the chalcogen sits on top of the red sublattice. And by doing that, we have created a situation, as shown here on the bottom, where the chalcogen atom is alternating across the vertical direction for the two sublattices, effectively creating our delta J perp parameter through anisotropy. It's now time for a few take-home messages. So we have uncovered a novel state of matter, a second-order topological magnon insulator in 3 dimensions, whose hallmarks are remarkably robust Chiral Hinge magnons. We have put forward a concrete experimental realization based on designer van der Waals heater structures. And this is very good news for magnonics, because now we can say that topological magnonics can go 3-dimensional.